Thank you guys for waiting patiently for this video. On this video, I'm going to be going over the technical breakdown of the printer and all of its details from build size to the laser power. On top of that, I'm also going to discuss how I'm going to divide the community into groups so that we're able to work effectively even though we have a larger community now. I know the first question a lot of people had was the build volume, and it's flippin' massive. We're going for 175 by 175 by 300 millimeters. And that's larger than the SinterLabs Fuse 1. But we've got some good news. We believe that we're going to be able to compact this large of a build volume into a printer that's only 450 by 350 by 750 millimeters. And in a second, I'll explain how we're going to do it. So most printers, like the SLS for All project and the SinterLabs Fuse, use a ball screw or a lead screw on the bottom in order to move the build volume up and down. However, there's an issue with this. The lead screw or the ball screw has to be at least the height of the build volume, meaning that you're having a massive extension in the Z direction, causing problems as far as space constraints. That's why the SLS for All is so tall. It has that big wide base with the ball screw and the lead screw sticking out underneath. So what we're going to actually do is embed the lead screw into the print volume. And you might be wondering, isn't that going to get jammed with powder? No. Ball screws are susceptible to dust, but lead screws are much more resistant. And the Micronics printer actually featured a submerged lead screw already. And that's going to enable us to massively save on Z height. Now these are going to be in the print volume, and the actual print volume is going to be 175 by 200 by 300. However, just to account for those lead screws, the advertised print volume is going to be 175 by 175 by 300 millimeters as mentioned earlier. We are going to go for a non-removable build chamber design. This is to simplify the mechanics of the printer and allow for increased insulation. The increased insulation should allow for less power draw and faster heat up and more consistent heating. This is just outweighing all of the cons in our opinion. Now, you might be wondering, well, how am I going to easily remove the powder cake? We are going to go with a two-door design. The front door of the printer will be thicker. It will be insulated heavily, and it will be what has the heater built into it. Now, that door will interface with a second door that is just the thin sheet metal front wall of the build chamber. Now, this front wall will be able to be slid upwards out of the printer. This will leave the powder cake there. Now, you might wonder, well, how are we going to prevent all of the powder from spilling all over the place? We are going to use a attachable bin design. The bin will be shaped like a box without a top or one side wall, which will then securely attach to the printer. Then you can remove the front wall of the build chamber and use a piston that will be built into the back of the printer using lead screws to push forwards the powder cake into the bin. From there, you will be able to slide back on the front wall to the build chamber and then slide on an additional panel to seal the powder bin. It might sound complicated, but I promise it's a lot more simple, and I hope to have illustrations soon demonstrating this concept. As far as post-processing goes, we are still looking into options for this. A sift bin might be an obvious answer. However, a more automated sort of design might be more effective. We're also looking at certain tumbler style concepts and things like that. Our goal is just to keep it compact and, most of all, affordable. Now, I said in my first video that we weren't just going to copy Micronics, and we've already shown that by going with a totally different footprint. However, it is still a desktop footprint. What we're going to differ more on is our gravity-fed spreader system. Instead of using an auger that's going to wear down over time or get jammed, we're going to have a top loader system so that you can directly pour in powder into the top and have it be gravity fed. In order to reduce clumps with this system, there's going to be vibratory motors mounted to the ramp. That way, a smooth transfer of powder is ensured. We also had to make the difficult decision of what type of laser we were going to use. The two options were a CO2 laser and a diode laser. Now, the CO2 laser was more likely to be consistent and more powerful, and it would also eliminate the issue with the dot of the laser not being perfectly symmetrically round. However, we decided to go with a diode laser. The reason is you don't need a whole lot of power. You're already heating up the powder to almost its melting point using the heaters. You just need a laser to push it over the edge. Now, the CO2 lasers are significantly more complicated and expensive. They also take up a lot more volume, and we're looking to have a compact desktop-sized machine, albeit a large one. So the choice was sort of obvious to go for a diode laser. Now, that will bring its own design challenges, but it's the most standard sort of laser being used. It's what was used on the Micronics, although they used a 5-watt laser. We decided to go with a 10-watt laser just to have a little more headroom. There's always room for this printer to grow. We are not sure what's going to happen down the line, and we decided that we would rather have a little more thermal headroom. Warping is inevitably going to be an issue, as the thermal delta between the different areas of the powder bed is going to cause problems. However, we have a solution for that. We are going to use PCB heaters on all 4 walls of the print chamber and on the bed. This will allow us to ensure even heating of the build volume. Now, some kind viewers actually pointed out that halogen bulbs have been used well before Formlabs patented the use of electromagnetic radiation heaters for additive manufacturing purposes. This means that we are going to stick with the halogen bulb system seen on the Micronics and the Fuse. This is just the most efficient way we can find it. However, we do have a backup plan if legal troubles arise or if we run into design difficulties, which is using ceramic heaters to heat the air around the build volume. This will evenly heat the powder bed and ensure that no warping will happen on the top layer. Here's where you guys come in. Now, we've already grown to over 75 members in a very, very short period of time. And myself trying to organize that many people would be literally impossible. So what I've decided to do is we are going to be holding applications for a head of mechanical engineering, a head of electrical engineering, and a head of software engineering. Now, these managers will then have the rest of the members of the community working under them, and they will ensure that progress is moving forwards and that things are being accomplished as they should be. That way, the load is dispersed and everyone is specialized into their actual interests and their expertise. I just believe this is the best way to organize it. So you can find the link to the application if you would like to be a manager in our Discord under the announcements tab. And I think that just about sums up this video. If you have any questions, I am super active in the Discord and I'd be happy to answer any of them. Have a great day.